In this video lecture, we are going to be simulating dynamically a double pipe or concentric tube heat exchanger. In the last video lecture, which you can find in the video description at the link below, we went through and derived the equations for this double pipe heat exchanger. This particular configuration is considering parallel flow, where both fluids on the outside and the inside are flowing in the same direction. By contrast, a counterflow heat exchanger, you would have fluid flow going this direction for one of the fluids and this direction for the other fluid. So that's called a counterflow heat exchanger. This one is a parallel flow or co-current flow heat exchanger. In this particular case, we're going to have this outer fluid, fluid 2, coming in at 800 Kelvin. So we're going to have T2 at the inlet is equal to 800 Kelvin. That hotter fluid is going to be used to heat this inner fluid, which is coming in at T1 at the inlet equal to 400 Kelvin. And we're going to set them up so they have different flow rates as well. The flow rate for the inner fluid will be m.1 is equal to 3 kilograms per second. And for this outer fluid, we're going to use m.2 is equal to 5 kilograms per second. So in the previous video, we went through and we derived these equations. So now it's just a matter of coding these in Python. So I've got Python pulled up. I'm using this Spider IDE as the interface. So I've already pre-populated some of this. We're going to consider a pipe length of 60 meters. The inner tube radius is 0.1, and the outer tube radius is 0.15 meters. So we're going to divide our system up into 100 equally spaced nodes and go from there. So here we're defining fluid flow for the inner fluid, fluid 1. We're just using water. We'll assume I know that water boils at these high temperatures, so let's assume this is pressurized water so it can get up to these higher temperatures. So we have m.1 of 3 kilograms per second with the heat capacity and density equal to that of water. m.2, just for instructional purposes, we're also going to consider water, but it has a different flow rate. We define pi. In the previous video, we also defined our cross-sectional areas. The inner pipe is pi times r1 squared, and the outer pipes, or that annular area, is pi times r2 squared minus r1 squared. So that is an annulus. So we've got our inlet temperatures defined here. Fluid 1 is coming in at 400 Kelvin. Fluid 2 is coming in at 800 Kelvin. So at the beginning, you'll see those two temperatures. Then we should see fluid 1 start to increase in temperature and fluid 2 start to decrease in temperature. And we would basically, at the end of our heat exchanger, we would see those two temperatures start to get closer and closer to each other. And our initial condition is going to be 300. So initially, both fluids throughout the length of the pipe will be at 300 Kelvin. And then we'll see as these hotter fluids, as the hotter temperature comes through, we'll start to see both of those rise. We're going to use U, our overall heat transfer coefficient, of 340 watts per meter squared per Kelvin. Okay, so there's still a couple of more parameters to define. First of all, we want to define our dx, which is basically our delta x, or the node thickness, or the node width. So because that's just going to be L divided by the number of nodes that we use. So that is in meters, and that is the node width. Okay. We're also going to need to define our simulation times. So we're going to go ahead and simulate this one for, let's go up to 1,000 seconds just to make sure that we reach a steady state, and hopefully we do. Okay, and we're going to take time steps of 1 second. You want to take small time steps so you get better resolution. If you take really large time steps, you may find, especially with the integration that we'll use, that this problem becomes numerically unstable and might blow up. So we try to use small time steps to keep things stable and accurate. Okay, so for future reference for plotting, we're going to define a vector of x that it's basically just going to be a vector that has the locations of the center point of each of our nodes. So we want our first node to be have a center point at dx over 2, and then we want that to go all the way until L minus dx over 2, and we want there to be n elements in this array, or in this vector. So we're going to define the initial temperatures. Our inner fluid is going to be a vector of 1s. It's going to be n units long, and then we're going to go ahead and multiply that by our initial temperature. So now we just have a vector that's all going to be 300s for fluid 1. We'll do the same thing for fluid 2. We'll just set it to that same initial temperature. Okay, we're also going to want to, we don't want that dot in here. Okay, we're going to need to initialize our temperature vectors. So we have dt1, dt, and let's just set these equal to zeros n units long. We'll do the same thing for the outer fluid. Okay, so far we're just initializing things. Let's go ahead and define our time vector as well. So this is going to be a vector that goes from 0 to t final in increments of dt. Okay, so now what we're going to do, we're going to set up a loop. So we're going to set up this outer loop of, so we're going to be starting at time 0 and actually starting at time 1 and just cycling through all of our time. So we're going to go from j in range from 1 all the way out to the length of our time vector. Okay, now this is the place where we define our energy balance equation. So everything prior to this has just sort of been setting up the code. So now the trick is going to be to code this into a big equation. So one method could be that we have another for loop where we loop through all the i's. So we start from node I equals 1 all the way up to I equals n, and we define this over and over again. It's actually a little bit simpler to just do this with vector math. So that's the method I'm going to take. So even though this video uses these i's, we're not going to do an I loop. We're just going to do some vector math to calculate this entire vector of temperature derivatives for fluid 1 all at the same time. So we're going to go dt1 dt. So this is going to go from node 1 to node n. So in Python, the indexing starts at node 0. So we're not actually doing the 0th node, which is going to be right here at the beginning. We're going to have to do a special energy balance there. We're going to do all the way from node 1, which is actually the second node, to the n, which is going to be node 99. And when you do this indexing, this later part is actually not inclusive. So this is defining it from node 1 to node 99, even though n is technically 100. It doesn't. So the way we've defined it, it's going to populate node 1 through node 99, which is going to take us from the to the end of our heat exchanger. So what I'm going to do now will basically be going and coding in this entire equation. So we've got our mass flow rate times CP1 times, now we're going to have T1. So remember, fluid is flowing into this node from the prior node. So we're going to set our indexing back by 1 here. So here we're going to go 0 to n minus 1, and that will represent the advective in term. Then we've got the advective out term, and now here we're going to go, if you remember from the prior video, energy is leaving this ith node, so we're going to have this match the same indexing as our vector. So this is going from node 1 to n. Just check our parentheses there, we look good. Okay, so now we're going to have our u times 2 times pi times r1 times delta x. And now we're going to multiply this temperature difference. So now we're going to go from T2, and again, since this is an energy balance on the ith node, that convective term is going to go from the outer fluid ith node into the inner fluid's ith node. So we're going to go T2, so we want this to match this indexing here. So this is going to be 1 to n, and then we're going minus T1, also nodes 1 to n. Let's just check our parentheses there. Okay, we're looking good. So now we need to go through and divide by our denominator, which is going to be rho 1 times CP1 times dx times AC1. Okay, hopefully we're all good there. All right, so this covers all the nodes starting with node 1, which is actually the second node, into the end. We have to do a different balance here at the beginning because that fluid is actually coming in from some other source. So here we're going to actually want to change our equation so that the in term for advection is this T1 at the inlet. So I'm just going to cheat and I'm going to copy this whole equation. But I'm going to go here and change this indexing. So here we actually want this to represent node 0. And it's going to come in. This in part of this is going to be T1I. And this out part is going to be T1 with the index of 0. And we want to replace both of these with zeros as well. Okay, and hopefully we're good to go there. All right, so now we've coded up the energy balance equations for the inner fluid. So now what we want to do is we want to go look at plugging in these energy balance equations for the outer fluid, and that's very similar. So here we're going to have, I'm actually going to cheat here and just copy this and modify it. So now this represents fluid 2. Let's put a line in there just to break it. So coming in, we still have M2. I mean, we have a different fluid. Okay, so now this is going to be the temperature 2. This term is still very similar. That heat is, it's leaving this outer fluid and it's going into the inner fluid. So the term is actually identical except for the fact that it's leaving that outer fluid, so we're going to put a negative on there. Otherwise, everything is still the same. Our denominator, however, is different. So we have rho 2, CP2, and cross-sectional area 2. So if you remember, this term came from this is part of the accumulation term. So for accumulation, we have to consider this annulus area because this is the volume of this annulus. You'll notice we're actually using R1 here because the energy is crossing that boundary from the radius of the inner tube. Okay, so similarly, the fluid in this outer annular region for fluid 2 is also coming in from some other source. It's coming in at this T2I, which is 800 Kelvin. So we need to take this guy and also modify it slightly so that it can include our boundary condition. So this 0th node actually has energy coming in at T2 inlet temperature, and then it's leaving at T2 at node 0's temperature. This is the same, except we want to replace this with zeros. Okay, so hopefully we're good to go here. All right, so now we want to actually do the integration. So we're just going to use this Euler rule to keep things very simple. So we're going to have T1 for the next time step is going to be equal to T1 from the past time step plus d T1 dt, so plus the derivative of temperature multiplied by our time step. Similarly for T2, this is going to be T2 plus dT2 dt multiplied by our time step. Okay, so this is all looking, hopefully this all works. We're going to generate a plot here. So we're going to plot x versus T1. Let's make this guy blue. This is our inner fluid. It's going to be colder, so blue would be a good representation of it. And let's just label it as the inside fluid. Okay, I think we're good there. On that same plot, let's plot our outer fluid, or the hot fluid temperature. So that's going to be T2, and let's make it red in color. And let's label it the outside fluid, or the outer fluid. I'm sure there's a better way of naming these. Okay, I'm going to define our axes. We're going to want our x-axis to go from 0 to L, and we're going to want our y-axis to go from 298. So we're just catching our, we know our initial temperature is 300, and then after that we're going to have an 800-degree fluid exchanging energy with a 400-degree fluid. So we should have an upper limit of 820, which will, thermodynamically, nothing can go above 800 in this system, so that should catch everything. Okay, let's go ahead and label things. So our x label is going to be distance down the heat exchanger in meters. And our y label is going to be temperature in Kelvin. Let's put in a legend so that we can actually see which line represents our inner fluid and which represents our outer fluid. I'm going to put this in the upper right corner for now. Okay, then we need to have a command to show our plot. And the way Python works, we have to put in this pause command if we actually want to see how our plot is changing over time. So we're going to put this plt.pause in there. And then Python also by default, so each iteration in time, Python is going to generate a new plot. So by default, it's going to keep stacking all those lines on top of each other. So we actually want to clear out those lines at the beginning of each iteration in time. So I'm going to do a plt.clearFigure. Okay, so in all likelihood, there's some error in this code. Hopefully we'll be able to identify it quickly. I'm not seeing any errors that it has caught by default, so I'm going to go ahead and hit play. All right, and there we go. Actually, this is working quite nicely. So you can see our cold fluid in the inner pipe is coming in at 400. They're both at an initial temperature of 300, so we start to see them gradually heat up. So this fluid is coming in at 400, and it's being heated by this fluid, where this guy, the outer fluid, is getting colder and colder as they exchange heat. So you can see reason that things are happening from left to right is because initially our pipe is at, all the fluids in our pipe are at 300, and then we're suddenly turning on valves and we're starting to introduce these new hotter fluids. So it takes a while for that fluid to make its way all the way through the pipe and gradually heat things as it goes. Also note that at the beginning we have this large temperature difference, but as the two fluids go along, you can see that temperature difference is shrinking as those two fluids approach each other in temperature. This is one of the reasons why a co-current flow heat exchanger is not always ideal, because the longer the pipe and the more heat exchange you do, the lower and lower your driving force gets for heat exchanger. This is in contrast to a countercurrent flow heat exchanger. So in a countercurrent flow heat exchanger, we have flow going the other way. So you can see near the end of this thing, we are getting we're getting this much smaller temperature difference. So it looks like we've basically reached a steady state. This is going to keep popping up plots, so I'm going to go ahead and interrupt the code with a Control-C. All right, so we've stopped our process. All right, so things are looking pretty good here. So another thing that we could do would be to evaluate what our Q is. So we could say, if we looked at Q1, that's going to be equal to M1 times CP1. This is after we've reached steady state. All that information is still embedded in the workspace of Python. So if we wanted to calculate the total amount of energy going into fluid 1, that would be M1 CP1 times T in our 99th node minus T1 inlet, and this is T1, okay. All right, so let's see what Q1 is. So Q1 would be 2.5 million watts, or 2.52 megawatts. So we should see that balance with the heat into in our outer fluid. So to calculate the heat leaving our outer fluid, it's going to be a similar calculation, except we'll start with the inlet temperature and subtract the outlet temperature. Okay, and you can see there's still a little bit of numerical error there, but basically the heat leaving our outer fluid is equal to the heat entering our inner fluid. So that's a nice way of seeing how much heat we're generating. So about 2.52 megawatts of thermal energy. And that is how you would simulate a double tube, also known as a concentric pipe, or a double pipe, also known as a concentric tube heat exchanger, dynamically using a software tool like Python.